and have a valid state ID. This gives us a set of attributes that can be used for access control. So in this case, the date of birth and a state ID or a driver license number can be used as an attribute for a group of students who can access a level 2 library resource without having to require their identities to be known in advance. So here's an example of such a policy. Note that the policy is not based on a given username. So an anonymous user can request a resource, and the ID of the user is an any keyword in the system. The user provides a credential for accessing resource level 2, and the attributes used in the credential are date of birth and DLN. So any user, as long as they are able to provide a credential issued by their original university or a trusted third party, indicating a date of birth attribute and a DLN attribute, will be able to access services at Purdue library or any other library who accepts those attributes. So we removed the problem of having to know the identity of the users in advance. And we also removed the problem of rule explosion in the policy, because this rule works for a category of users who satisfy these attributes. Similarly, we have a role credential, and a role may also have a credential type. The motivation for having a role credential type can be seen in this example. We take the example of a federated digital library once again and consider two roles in Purdue database. There's a borrower level 1 role and a borrower level 2 who can borrow resources belonging to level 1 or level 2 respectively. So consider a borrower level 2 role, and suppose Purdue wishes to exercise different policies for a grad student in that borrower role and an undergrad student. They might say that a grad student can access books from anywhere on campus, whereas an undergrad student can access books only from inside the library. And you may have noticed that this constraint is actually enforced in our libraries when some books are actually on the reserve desk, and you can only borrow them while you're inside the library. So what is the solution to this problem? One solution is that you can obviously create 2 additional roles. You can say level 2 grad and level 2 undergrad and enforce a separate access control policy. But this will clearly lead to the problem of rule proliferation. So the solution that we use again is the use of attributes. A level 2 role will have a credential for borrower level 2, and the credential will have attributes, class, and location. Based on the value of the attributes of the user who is in that borrower role, you can design the access control policy rule. And we will see an example of that shortly. Before going there, we'll discuss the third credential component in our language, which is permission credential. As you might expect, a permission credential has an object and an associated operation. But what's of interest here is the propagation option on the permission. The propagation option becomes interesting in the case of XML documents, because XML documents are hierarchical in nature. So if you give the permission to the top level element, it may or may not propagate to all the child elements. And so we have 3 different options. Either the permission propagates, does not propagate, or it propagates only to the first level element or all the elements. An example of a permission that we discussed before is a get permission on a level 2 resource. And we use the HTTP get operation in this permission. So coming back to the assignment rule, assignment rules are the second kind of components in our policy language. The key in the assignment rule is the use of the assigned constraint element. And this is what differentiates an assignment rule from an all or nothing kind of an authorization. Because in an assignment constraint, you can specify assignment conditions based on the credential type that the user or the role is associated with. So here's an example. The role libborrower level 2 can be assigned to any user if the user supplies the resource level 2 credential having a DLN and a DOB attribute. And the condition there is that the credential should have non-null values of both of these attributes. And the logical expression tells us that both of these predicates must be true for this role assignment to occur. Similarly, a permission to role assignment rule A level 2 resource get permission can be assigned to a lib borrower level 2 role if the role has a lib borrower L2 credential. And you notice here that the logical expression has an OR operand, which means that either the class is graduate, which means the student is a graduate student, or the location is inside the library. This solves the problem that we discussed earlier, that for instance, if Purdue wants to enforce an online access to its library resources, we can use this policy to allow a role to access the service, provided that either the user who is in that role has a class attribute equal to graduate, which means it's a graduate student, or the location from where you are accessing is inside the library. So if you note here, the location is a dynamic attribute, and we need runtime evaluation of a dynamic attribute. So this is something that we have recently extended. We have recently extended our architecture to provide support for location-based constraint evaluation, where we use a geospatial profile of role-based access control model, and we evaluate that at runtime to determine the actual location of the user, and the decision of that access request evaluation is fed back to our access control processor, and we accordingly assign the permission to the role if the user belonging to that role is within the authorized location. So that's a pretty cool concept because it has a lot of application in pervasive computing and mobile computing area. So moving on, the next component is the constraint definitions. Constraint definitions allows us to enforce interval, periodicity, or duration constraints on any kind of event. And the event that we are concerned with is the user to role assignment and permission to role assignment. So to give you an example, this constraint definition defines an interval starting from 1st of January 2005 to 31st of December 2005 with a duration of 1 week and a periodicity of first week in either the 1st, 4th, 7th, or 10th month of any year. If you notice carefully, this periodicity represents the first week of every quarter of a year. And this goes back to the requirement I discussed earlier, such as in financial systems, where your billing cycle might be every quarter, first week of every quarter of every year. And if you want to constrain the authorization of someone based on a billing cycle or based on any quarterly cycle, you can enforce this constraint in your access control policy to minimize the exposure of information for potential unauthorized or unacceptable use. And no other policy language has such sophisticated temporal constraint capabilities. So here's an example of an assignment rule previously discussed, but this time with constraint. So we use the same example as a lib borrower level 2 role being assigned to a user, but this time we include a periodic time expression ID. And note that this ID refers to the constraint that we have defined earlier. So what this means is that in addition to satisfying the credential attributes that the user has provided, the temporal constraint must also be satisfied for the assignment to occur. And you might notice the flexibility requirement is met because you can include or exclude the temporal constraint according to your own requirements. All right, so we have discussed the policy grammar and the policy components. Let's go to the UML Meta-model. UML Meta-model involves mapping the X grammar into UML and translating the UML into UML schema. The motivation for the former is that it allows application of existing software engineering methodologies toward policy development, which facilitates our goal for policy engineering. And the second part allows rapid translation from XML schema definitions to program code, which is once again a key requirement in federated systems, going back to our initial development methodology concerning deployment and integration of policies in federated systems. For translation of UML into XML schema, we use UML profile